Hello everyone. This is a really quick video on how to assign aromatic protons when you're dealing with benzylic derivatives. This is for Chem 143b, Experiment 1A or Experiment 1D. And from my understanding, it's like everyone's like intro to NMR. And so I can get why having not done NMR and looking at a real spectra, it can be a little bit daunting. And it's totally valid, but hopefully this video can clear up some confusion. And also my apologies for not the best microphone. I know it's probably going to be sounding really bad. But without further ado, let's kind of begin onto what I would do if I had to annotate an NMR. So typically what I do before I even get the NMR spectra is kind of just start to figure out where things should be before I can even put peaks and ppms to an actual signal. And in this case, what I do is I just draw up the molecule and I give it my best shot at annotating it beforehand. And so here is our benzene ring, and our compound has an aniline attached to it. It has a nitro group attached to it, and finally it has a bromo. I like to draw out the entire molecule showing the actual double bonds as opposed to a circle. And additionally, I like to show the nitro group with its actual double bonds. And the reason I do that is because it actually helps explain what I should expect on NMR pretty well. And so first, when I do NMR, I like to also label all of my hydrogens to identify whether or not they're chemically equivalent. And in this case, that's just completely dependent on symmetry. And so in this molecule, there is no symmetry. If I break it apart in any way, there's going to be nothing. So I'm just going to call this HA, HB, and HC. And so the first thing I like to do is think about, once I've done this, okay, where are these things going to be on the actual NMR chart? And so for reference, most aromatic or benzylic protons are between 6 to 8 ppm on your NMR. And on an HNMR. And so what I do to distinguish if something is going to be closer to the 6 region, so let's say here's 7 as a midpoint, 6 and 8, what I like to do to distinguish whether or not I suspect a proton to be closer to the 6 part of the aromatic region than the 8 part is to try to figure out what proton will have greater electron density and what proton will be having less electron density. In other words, which one would be shielded and which one would be deshielded. With greater electron density, the electrons oppose the magnetic field that the NMR adds to it. And so what you'll see is that you're going to be more upfield. And so here you're going to have more electron density. So increased electron density means more upfield, and lower electron density means you're going to be more downfield. And that's meaning, closer to 8 ppm and another one closer to 6 ppm. So with the compound that we have, what can I suspect to be closer to the 6? And what can I suspect to be closer to the 8? And what if it's in the 7 mark? So we'll see. And one thing I like to do to figure out what will add and what will remove electron density is really resonance. Where resonance, you're actually moving electrons. In induction, which is through sigma bond donation, it dies off relatively quickly. And what I mean by that effectively is that the impact of induction isn't as significant from across the entire molecule as is resonance, because resonance can impact many bonds away, whereas induction is really localized to maximum of 4 bonds, but typically it's 3 because, and it's most influential 1 bond away, of course, but so keep in mind, resonance is more impactful than induction. And if you can't explain something anymore by resonance, then you should try to explain it through induction. So without further ado, let's begin. I like to start off with aniline. If you remember anything from Chem 41b, that aniline is an electron donating group by resonance, but inductively it's electron withdrawing. But since resonance, as I mentioned, is stronger, the aniline's pi donation is going to be more of a significant contributor to seeing chemical shifts. And what happens is that these lone pairs will add into the ring, and then what happens here is that you're going to form delocalization. First, you have this double bond that's going to break, and it's going to go onto this carbon right here. So the ortho position. And then let's say I build up negative charge, and I'll draw this more clearly here. Hold on. So here is my aniline. And I have negative charge here. And what I'm going to do is move it over and break this into here. I'm just drawing resonance contributors, and that's effectively how I get a lot of this done, is by drawing resonance contributors here, and you have the bromine here, and you have this double bond. And finally, you're going to get this and add here. And this is actually the key to this experiment, to figure out one of the proton positions or chemical shifts is actually this guy right here. Okay? And so all I've done is essentially is delocalize the electrons, and I just drew the resonance contributors. But what's important is to note that, oh, this carbon, which also has this hydrogen right here, is going to have greater electron density. And if you recall, greater electron density means you're going to be more upfield because you're opposing the magnetic field that the NMR machine is applying. And so as a result of that, and I should actually be drawing more appropriate resonance contributors from here. But what's important here is that resonance is greater than induction. Even though all these groups are inductively withdrawing, the resonance is more stronger. It's added to this area, and it's going to push this proton closer to the 6 mark. So I can imagine what I've labeled as HC to be somewhere here, okay? And for a general rule of thumb, if you have an electron donating group by resonance, the positions it's going to impact are going to be the ortho and para positions. If you recall from what makes a ring activated and what positions get activated for the regiochemistry, it's the ortho and para positions for this same reason, because you can have better delocalization of a charge here. Now, what about the other two protons, HB and HA? Well, then I recognize that, they're not going to get impacted by greater electron density. Could they possibly be impacted by reduction of electron density? And reduction of electron density comes from electron withdrawing groups. And so I do essentially the same thing, but this time I just draw the resonance contributors if the benzene ring was donating into the nitro group. And so that's exactly what I'm going to do. It's nothing complex, and it's relatively straightforward stuff, but without further ado, let's begin. So you're going to get this donation right here. This donation will do this. And although I know that some people will argue that you can add electron donation into here, and that's significant, ignore that for now, because what does that do for the protons on the benzylic ring? It does nothing, right? As opposed to, in order to understand the electron density there, it does nothing to understand it. So then you can say, oh, this is going to move up, and it does so. And you're going to get a contributor here. Oh, actually, I'm drawing this wrong. There we go. Oh, would you look at that? There is greater electron density here. And if we recall, that was our HB, because it's ortho to the bromine group, and so there's positive charge there. And actually, this double bond will go ahead and delocalize, and I'm actually going to build up positive charge here as well. And so, rule of thumb for electron withdrawing groups by resonance, if you're an ortho or para position to them as well, you are going to have increased positive charge, meaning you're going to be upfield. Okay, so electron withdrawing, ortho para, are going to be not more upfield, my apologies, more downfield. More downfield. And additionally, electron donating by resonance, again, all these are by resonance, you're going to get ortho-para positions, but they're going to be upfield, okay? And so now I can go back to this little chart that I drew and say, okay, well, I know that this nitrogen group is here, and the ortho position is HB to it, and the para position, the ortho position to it is HA, and the para position to it is HB. And so I'm going to list HA and HB as going past the 7 mark. Okay? And so now I've kind of said, okay, I can distinguish between these two guys, but how am I going to distinguish between HA and HB? Because clearly resonance can no longer define which one would be more upfield or downfield. And so the next thing that you should go to is typically induction. And this is only strictly speaking for chemical shifts. If you can explain something through chemical shift, great. If you can't, then there's something else that you should go to, and I'll explain that in a second for this particular issue. So when I go to induction, and I'm going to just redraw everything out for the sake of, I'm going to redraw everything for the sake of just being organized. This time I'm just going to draw it as a ring like that. I just want to mimic it. NH2, NO2, Br. This is HC, HB, HA. Okay, so now that I've recognized that HB and HA are going to be past the 7 mark, what do I do now? Well, I go to induction, and that's the next thing that anyone should do really for describing NMR shifts, or for NMR chemical shifts of non-equivalent protons. And so in this case, right, you look at HB and you look at HA and you say, well, okay, they're both equidistant to the bromine, so they're both going to have electrons pulled away from them towards the bromine, so that does nothing. And then what you do is you look at the nitro group and you look at the amine group. Well, in both cases, HA and HB are going to be meta to the amino group, okay, which is an electron withdrawing group by induction as well. And so you'll say, okay, well, the amino group doesn't help distinguish anything, but finally, the nitro group does. The nitro group, by induction, is pulling more electron density from HA because it's only ortho to it than HB. And so I can safely say that there's probably a good chance that HA is going to be even further from HB. And so chemical shift-wise, I'm going to do this. Well, actually, I'll do it up here. Chemical shift-wise, if you just pay attention to this bottom right corner, I can say that, okay, well, HC is going to be at the very end by resonance, and greater than that is going to be, what do we say? I forgot for a second. Yes, HA will be greater than HB, and so it goes A, B, C in my diagram. And the reason this works, obviously, is because these two versus this guy can be explained through resonance, and these two can be explained by induction, primarily through their proximity to the nitro group. Everything I've said so far can be applied to other benzylic protons, but there's something else I want to introduce to you, and it's ortho-para and metacoupling. Not really para-coupling, but ortho and metacoupling. So if you recall, there's the N+1 rule that works perfect for ideal spectra. But, in the real world, most spectra aren't perfect, and this is especially true for benzylic rings. Benzylic rings do not obey the N+1 rule where you have to be 3 bonds away. As a matter of fact, you get metacoupling, which is 4 bonds away. And so what do you do then? Well, in the case of our structure, and I'm not really going to go into why this happens. It really has to do something with bond rotation and angles, but that's beyond the purpose of this class. If I were to draw, actually let me redraw this similar to the last structure. If I were to draw this compound, I'm telling you right now that ortho and para positions ortho and meta positions couple to one another. What do I mean by that? So I'm going to draw all these H's out again. And I'm just trying to be consistent. This is HA. This is HB. Finally HC. So if you recall, coupling is when adjacent, or rather non-equivalent and relatively close by protons are going to be in different spin states, and these spin states couple to one another and create multiplicity. I'm not going to go into depth about what's the cause of that. Go read a OChem textbook if you need help with that. This is supposed to really just help you with experiment 1. And so when I'm going to figure out what the splitting pattern for this is, I first recognize that, okay, all these are non-equivalent, so they're going to split one another. So first I say, okay, well, let's start off with each proton and try to analyze it. HC, what is that going to get split to? Well, you have to do the ortho-meta coupling rule for benzoic rings, meaning that if you're at an ortho or a meta position to the proton you're looking at, you're going to couple to it effectively, or you're going to cause it to have a splitting pattern. So the only thing that is in an ortho or meta position to HC is just HB, right? Because that's ortho to it. And so I can say that HC is going to be a doublet, okay? What about HB though? HB has two things. It has HC coupling to it, but it also has HA coupling to it. And that means that it has both ortho and meta coupling, meaning that it'll show up as a doublet of doublet. And finally, what about HA? HA, if I look at it, well, it only has it only has a meta position, and that meta position means that it's only going to be a doublet. And so from here, I've deduced that I can probably tell you, without even looking at chemical shifts, I can tell you I know what HB is going to be, okay? Besides using that chemical shift analysis that I did. And each of these things, these couplings, have a specific J hertz to them. These J hertz values are actually super indicative of whether or not you have that form of coupling. And so you can basically precisely prove that, oh no, I know for a fact that this is going to be ortho and meta coupling because of what the J values are, and they're associated to each type of version. So ortho coupling is going to have roughly, I believe, like somewhere like 6 to 10 hertz. This is, by the way, like rough numbers. So O equals 6 to 10. And meta is like 1 to 3 hertz. And so when you look at your NMR, actually, you can prove that. And here's a NMR of my friend. But with that being said, I can tell you how to detect that. And so this is on Maestra. When you go to Maestra, you can basically just go ahead and look at, let's say this guy. It says it's a doublet of a doublet, and I'm going to go check that. And all you have to do is click on this color right here to open it up, and it tells you J. J equals 8.8 and J equals 3. And so that follows into the sixth. I can say that, well, that 8.8 is from the ortho coupling, and that 3.2 is from the meta coupling. So that's another way that you can characterize your NMR spectra and be kind of definitive about it. Be, more conclusive that a single that the spectra you're looking at and the peaks that you're assigning are actually really from the actual protons that you're looking at. So go ahead and do that as well. And that's basically it on how to assign this actual structure. What I do want to recommend, though, for future reference, is to actually take advantage of ChemDraw. So you don't have to watch the rest of this video if you don't want to, but ChemDraw has a really unique benefit to it where you can actually use ChemDraw to create for you spectra, kind of, like rough spectra. Don't use ChemDraw as an end-all, be-all tool, but at the same time, go ahead and use ChemDraw to your advantage. And so what I do is the following. I just draw my compound. So let me just make what I have here. Boom. 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 Boom, boom. 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 Okay, this is the compound I have, and once you make it, what I want you to do is grab this grabbing tool, basically highlight it, and then I believe you want to go to, there's a specific thing that you can do on ChemDraw where you can go to structure, and then you can go to HNMR. You can also do C13 NMR, but in this case, we're only doing HNMR in this class, and it actually predicts it, and it does exactly what I said. And it assigns these things. It tells you the relative quality of it, and it's not the best, but it's all right. And you can do that to kind of confirm your belief of what you think a spectra should be. Another thing I'd like to know just about basic NMR literacy is that a lot of the stuff we're doing in this class, based off what Professor Wiseman has told me, is crashing out solvents. And so to do that, if you have really nonpolar stuff, you're going to use a lot of water. Water is at 1.55 to around 1.6, okay? So whenever you see a singlet of 1.55 to 1.6, it's a great chance you probably have water inside of your product, okay? And so whatever you do, you just label this, or you go to click on this big purple box and you go to the name and you just call it water. And you don't really have to worry too much about it. And again, this is not my spectra, so don't use this as an end-all be-all. I don't even think this is pure, but yeah, that's how you label NMR peaks. In the case that you have an impurity, I would recommend using ChemDraw heavily, or also trying to find Googled spectra of the NMR and try to cross-reference your thing and then see what the other impurities are, because that probably is from two things: unreacted starting material that has basically bled through from maybe previous reactions or just the one you did previously, or subsequently it's a daughter impurity, meaning that one of the reactants that you had in your original reaction, or one of the subsequent products and future reactions, they've reacted with the stuff that you've done now and they've created something different. That could be an issue. And those can completely skew everything up. So if you have more peaks than you expect, the first thing you should typically do is assume they're solvent and try to figure out what you can attribute that to. However, if you can't do that, they're probably actually impurities, and characterization of that can be a completely different thing than what I've just described to you. I've only described to you how to do the actual product, and that'll basically necessitate more care, and it's actually a relatively difficult process. You have to isolate the impurity. But that's all. I hope this video was insightful, and hopefully this helped you out. Bye-bye.